that is working. So as we already had arrays in the last lecture, I think that was the last lecture, yeah. Then you already have seen that we don't only need to work with things that technically fit into one register, but we also can have a larger block of memory which is made up of elements where every single element in principle fits into a register. So like in the array, every array member you could put in a register, while the whole array would not fit into your typical registers. There are some special registers where you can load arrays up to a fixed length, like with the AVX instruction set. AVX 512 is capable of taking arrays of different word sizes, where the total amount of data loaded at once is 512 bits. So you can, how much is that if we divide it by 8? 512 by 8. So you can have up to 64 character elements, and those extensions are used for vector operations. So pretty much what in the past was mostly done for good performance on graphics cards, to some extent with modern Intel and AMD CPUs you can do directly on the CPU, which has various benefits, mostly because it's more flexible, but you are limited still to make vector operations, so a lot of operations of the same type. While when you're operating with normal generic purpose registers, you can do any operation, but always only on one element. But aside of this special case where you can load an array into a register, the general purpose registers don't take arrays, only individual machine types. And with structs, you have a similar idea like with arrays, where you have multiple of those machine types. You can also, of course, have more complex structs containing other structs, for example, but we'll look at in a second. But the simplest struct you can create would be something like this. My struct. So the general syntax is you write struct, then you write a name, and then you can in brackets specify the member variables. So let's say int var a. So this will be 4 byte, and instead of an array where all the elements are the same, and of course, so in contrary to an array where all elements are the same, here you can have different types. So the next type can be, let's say, an int 64, for example. Let's call it var b. That's 8 characters in size. One main difference also is here that while that arrays, normally when you operate with arrays, you can create them of arbitrarily size. You just tell the compiler or the heap manager how many elements you want, and you will get an array of this size. While with structs, a struct has always one exact fixed size. At least with regard to normal C. With C++, you can have templates, which we will take a look at in due course, where you would end up with structs of different sizes. But that's a special case. For what it's worth, for normal just C without the plus, a struct always has a defined size. So let's add a few more characters, and then I will show you an interesting phenomenon, and we will see if anyone can guess why it is as it will be. So let's make a short variable d. Oops. That's 2 characters, 2 bytes. Then let's make another char. That's good enough. So that's our structure, and we can now use this structure, this type, as we would normally use any other type that we have at our disposal. So we can write my struct instead of, for example, int or something, then we call it vars or whatever we want. And like with an array, we can initialize the initial values and using the brackets. This is, of course, you have to be careful with this, because with an array you always have just the linear progression. Here you have variables of different types, and when you have structs, you might want to add something, so or remove something. So let's say at some point variable this becomes obsolete, so you remove it, and then of course if you initialize something like this, you will need then to, which one was it, to remove the right element. Sounds easy, is easy, but of course since it does not have any checks from the compiler side for correctness, it's extremely error prone. So it is generally discouraged to initialize structs in this way, unless you're only just initializing everything to 0, or what is, for example, customary in the Windows API is that the structs often start with a first member t size t, which is then the size of the structure. So the idea is here that if you are passing a structure to a operating system function and tell, so instead of using a second variable where you tell the operating system how large the structure currently is, you just already use one field of the structure to do it. And the reason why the operating system wants to know this is because new parameters may be added later on to the structure for in newer Windows revisions, for example, and instead of creating new APIs every time, it is much more convenient to just reuse an existing API, which then just checks, okay, how much space do I have, and then okay, I know I need to set those fields, and I should not try to set the additional fields because this would not be valid. We will take a look on this on such behavior here as well a bit later. But as said, like initializing with some size, for example, that would be such a use case where you initialize the size with the size. But any more advanced initializations, as already mentioned, because of the fact that you don't have any validation whether you are assigning the values to the fields you intended to, is discouraged. In other languages, you in fact can use these brackets with the names, so that you tell like name, comma, no sorry, name, double point value, comma, next name, double point value, etc. In C, at least in the version we are using, this does not work. So so let's go back to the not recommended version. And now if we just put a breakpoint, let's give a, I heard something, yes? Yes, I'm forgetting to do that. No, that's too big. Is that fine? Okay, so here we can see in the locals that we see all the variables and the values we have assigned, and what we now also can take a look on is how large this structure is. I mean, in principle we could count like 4, 12, 13, 14, 15, 16. Wait, is that correct? Shouldn't be. Wait, 4 und 4 und 8. No, that's fine. 16. It counts like 16. It won't be 16. You will see that in a minute. Const int var1 size is size of var. And if we, since it's a const, we see that it's significantly different. And the reason why it is different, why it's 24 and not 16, is called memory alignment. So the idea generally is that if you are accessing, I already I think told that the last time with regard to some other things we saw with the compiler, that for optimal performance you want to align your memory, the data in your memory, such that the CPU can easily retrieve the data in one block. It doesn't have to like go with 2 overlapping blocks and then go select the right offset. So this adds overhead, which is very bad. So typically such structures by the compiler are aligned to whatever is the largest, so either to a 32-bit boundary or to a 64-bit boundary. So in principle, in reality here at this position, the compiler has inserted a variable of type int, which does not exist. I mean, does not exist. It doesn't have a name. The space is there. It will never be used for anything, but it's there, and the reason is to align the access to this variable with the 64-bit boundary. And in the same way, it will here add another 4-bit byte shadow variable, or dummy variable. I'm not sure to what extent the compiler would then try to optimize that away if you would have multiple structs after each other. We could test that later. But in principle, if we then try to write that down, the whole thing, so in reality this 24, and in reality it would kind of look like this. So oops. So we have here the different bytes of our, so from 0 to 7 for the 64-bit alignment, and you see where the compiler always added empty space. And if we would add here EF, for example, that actually the compiler should still be able to just shift that. So the structure will then still be the same size. It still should be 24. Let's check that. Hello, yeah, 24. So in this case, we just added here F, and this, and the empty space got just reduced. But since that's not part of the original demonstration, let's why not? Let's leave it in. This memory alignment of structures is important to know because if you try to allocate memory for a structure, you may not always. I mean, you should always, of course, use just the size of operator. But if you want, for some reason, to write down a number or something, then it's important to know that you cannot just count the members together. Another use case where it might be also very important to realize that there might be unlabeled empty placeholders, dummies. Sorry. Okay. Is yeah. It makes sense. So if you would exactly, yes. So this is one use case where this is helpful. This allows you to create smaller structures. But another use case is that if you have a large structure for which you might not necessarily have the full definition, and then you want to find some parameter somewhere and just access the one parameter, then what you could do, for example, let's say we can demonstrate that. Let's say we want to access the value d, which should be, it's 1, 2, 3, the fourth one, that should be 4. So since we already had pointers, we can use pointers to create a char ptr, just a pointer on our array, and here, although that will not compile since it's the wrong type, so we need to tell the compiler that it's fine. Okay, and maybe we want to access this one, that should be then 4. And then the idea would be that if you want to do that, you can write here the right offset, which would be 16, no sorry, 4 and 8, 16, 17, 18, 19, 20. Wait, is it 20 or is it one less? Let's see if 20 is the right one. And of course, for such operations, that was it the right one? 5. That was this one. Yeah, that was the right one. Perfect. Because the last one is 0, since we have not provided a value for it. Yes. So you can access members of this array like this, just knowing where they start. And in various use cases where you might know the structure but don't have like really the up-to-date definition for it. So for example, there are some not documented operating system structures in Windows where it might be useful to get some informations out, but you don't have the headers for it. And if you know, okay, this will be at a given offset, usually at the beginning, and you don't care and you hope that it will not change too much, and you can try just accessing by offset instead of creating. I mean, the other strategy would of course be to create some dummy structure which just shifts all the offset to where you want it to be. So we can demonstrate it with another structure. So you would just create like my struct1, let's call it. And then let's say we know we have an int and an a and int b. Sorry, it should be Strichpunkt. Then we don't care. I mean, we can even make int64 dummy1 dummy2. That brings us here, and then we want to shift it by 3. So let's say char dummy3 is array of 3, and here is char my value. I'm interested in. I'm too lazy to type it out. And now what we can do is we can just we have this. Let's call it no test2. That should be a pointer. And then we can use either this or pointer, doesn't matter. Let's go with that one. Sorry, that should be here. We need to cast it. And a couple things to say about arrays. About structs. If you want to access a member, and it is defined here, so it is defined on the stack, then you do it just by using a dot. So let's say int test3 is equals dot, and then I don't know, let's take a. While if it is a pointer like here, okay, so we wanted to access the number 5, right? So let's say we are accessing this one, char. But if you want to access something that is a pointer, test4, then you need to use the arrow operator. Wait, var is false. Test5 is richtig. Then you need the arrow operator, and in principle, this arrow operator is equivalent to dereference test5 punkt my value. So this is, maybe we should write it as a line. These do the same thing, it's just more elegant. But the point is that you can create some dummy structure. You just need to have the right offset, and then you can access it like here from the structure, and you don't really need to care about the structure of the structure before what you actually care about. So let's run it. You will get the same value here. So that was 5. Oops, that's not good. 1, 2, this is 8 and 8. Then here we want 3, and the 4th one we are interested in. That should have been correct. Either something's not right with the alignment, or oops, the size of this is 24. That should have been, so 4 and 4, yeah, that should have only added a dummy at the end, but this should have been at the right position, and this should be interesting. Let's investigate it further. We can, for example, then just check data variables of our structure. So we don't care for the dummy. The dummy 2 became 2. This dummy has 3, 4. Sorry. That looks, however, almost. Actually, it looks kind of right. Why is it then wrong? Because the fifth one is 5. And here it worked as well. So what we can do is we can try to find out the offset that this thing here tries to have. There is this really nice template. Do we have that here now? Offset of structure is so first we take this one, and then we say member we wanted the variable e, const int that should evaluate. Okay, so that's at offset 20. That's what we did. That's fine. And now we check it with our dummy structure. We want my value. That should be another number, of course. Sorry, another letter. 19. Okay, we somewhere lost one character. Why is that? Actually, 20 is one too much. It should have been team. One moment, please. Let's take a look into this variable. So we have our pointer on test1. So oops. So 0 is 1. This is correct. The next 4, well, actually more. The next should be all 0. So 1, 2, and so on should be zeros. The next non-zero should be at position 8. This is correct. 8. This goes then to the end. This is the whole thing. Then the next one after 8 is 16. Should be 3. Doesn't type with the mouse here. 16 should be 3. 17 should be 17 should not be this. So this, so apparently the compiler decided to align a different 17, 18. 18 is 4. So actually the compiler did it slightly differently. It decided to align this short access already. With Visual Studio 2019 it did not do that. So it made a dummy entry here. This shifted down so that this is aligned. This is then 1/3, and this one will be only 2. So that's, yeah, that's what the compiler did. So this should be 19. Sorry, 20 was fine. 20 was fine. But if this the compiler did this, then here we will need to also go 1/3 if you want to go to the e value. So this will be 4. So we could just have an int here. Dummy 3. Now this should be correct. Yep, now it's working, and now the offset of both is the same. So yeah, you see it's easy to make mistakes when trying to figure out where exactly in memory something will end up, but normally this does not really need to be done by hand. So normally you have well-defined structures, and then if you need an offset, you can just go with this macro, which already is provided by the compiler. So this is a reasonably nice way to find out the right offsets without counting. But as said, it's good to remember how this would be aligned in memory, just in case you don't have the macro or want to do something particularly unrecommended. Yeah, so as you already have also seen, you can cast any structure to any other structure if you use pointers. It does not matter. Sorry, where did we do it? Here, for example. So it doesn't matter in the list. We could also have here just this structure. You just need to tell the compiler, and in the reference on that, You just need to tell the compiler that you know what you are doing, and then the compiler will just allow you to do it even if the structure is completely incompatible. So in this case, of course, it was compatible after we fixed it, but you could cast from one structure to another and then just get garbage data out. This is perfectly easy to do and should be avoided when possible. That's of course also why the compiler, if you would not tell him to explicitly do it, would now complain and mark this and decline to compile the code. Yes?
Just for understanding or for clarification, this line casts 1, 2, 3, 4, 5 on the constants in the second struct, right?
What do you mean 1, 2, 3, 4, 5?
That's what in bars is stored.
No, it casts only the pointer. So for the compiler, every pointer is just an address in memory. But if it knows that the type is different, it will not allow you to copy it. But if you add the explicit typecast, so if you go with, for example, this value, then it will in basically just copies this number from this memory location to this memory location, but it allows you to do it. If you would not do the cast, it would not allow you to do it. And the important thing is that if we now would, for example, change this variable here to, let's, I don't know, 50, then in our original variable, the field, what was it, var e, would also change to 50. You can run that quickly because we are operating here with pointers. So as you see, we initialize it with 5, but now if we look on, where was it, vars e is now 50. This line, through accessing a pointer plus an offset, what it basically just did is it overwrote the data with which we initialize this variable. And this override can be done also really just using directly the offset. So we can take again the memory address where it is in, cast it of course to a character. Now we can add to it an offset of what was 20. Then we can dereference it, so tell the compiler at this number that we get here, access the memory at this location and assign it the value, I don't know, 55. And if we do that, we will also end up with our var having the value 55 now. This is important because using pointers, using the memory addresses of an object in memory allows you to give various functions access to this object. So when we later during today's lecture will take a look into functions, I will show you how you can, for example, get more than one return value by just giving to a function a pointer to a structure, and then the function inside can modify any field of the structure. But the only thing it got was one, in this case, a 64-bit number that tells it where the structure lies in memory. Is that clear, or are there still open points with regard to what we just did here?
I think I had a thinking mistake. Like it's not, I don't understand it for 100%, but I think my mistake was I thought that the line mystruct1 star pointed some values in the from the first struct. But like could you do this? Could you appoint values stored from the first struct? So in the vars variables, so 1, 2, 3, 4, 5, you could cast them onto the second struct as well, right? But you didn't do it. I thought you did that.
Well, with the typecast, you are only casting the pointer and not touching the data at all. But of course, what you can do is, if we would add here, and what you, for example, could do is, we could take vars.var b is a 64-bit value, so we can take a reference on it and cast it on int asterisk, oops, and then have a int asterisk okay, and now we could access 0 row and one is the hide word. So you can of course cast so basically what happens here is you take the address of var, you add to this address like we did here the offset, just that in this case the offset is 8, not 20. You add to it the set offset, so you have another number, and then you store this number here, and then you can either access the memory exactly at the number, so +0, or you can access it +4, since it's of type int, and the array increment will go in steps of 4 byte, and then you can access the other field. So you can in principle create pointers to any memory location. The memory can be just a single variable, it can be a structure, it can be an array, or it can be one field, one member of a structure. So, or it can also be a pointer to classes, but how classes work we will take on a bit later when we start with C++. Um,
Yeah, the last example is clear. I was just confused by the. I think I didn't look at the variables you used, the test2 and point and ptr. I was confused by those. Like the one you just said, that's clear.
Okay. Gut. Where are we? Yeah, so we had this. Yeah, so let's take a closer look on what I demonstrated here already. This referencing and dereferencing. So as said, when you have just a normal structure like this vars initially, if you want to access a member field, for example A, you just do it with this dot. For classes it is the same thing, but that's I said for later. And if you have the pointer, so let's again create another pointer to this. It was my struct here, my struct asterisk piv vars is equals, then we take the reference on vars. And now if we want to do the same thing, if it's a pointer, we need to set this arrow operator. The nice thing is that the compiler, once we type the dot or the arrow, will tell us what member variables we already have to pick from, so we don't need to type them out. And what of course can also be done, you could make a pointer on a pointer. So this is the, let's say, convoluted things about pointers, that if you have a memory location which stores a memory location, and nothing prevents you from having yet another memory location that stores the memory location of a memory location. So in this case we would then just take a reference on this. So now we have basically a pointer to a pointer, and if we want to get to something from this pointer, then we of course would need to first, so we cannot do this because it's a pointer just on a pointer. The pointer itself, a standard pointer, does not have any members, so we need to dereference it. Oops. And then we can access the member variable, or what we also could do is we can dereference one pointer, then dereference the other pointer, and then go with the dot. Generally this approach is not recommended because it's quite nice to see through the use of the arrow operator that we have a pointer with which we are working right now. So I would not recommend to use this to dereference the last thing. So if you have a pointer to a pointer, you have to, but once you arrived at the, let's say, top level of your pointer hierarchy, then you should just use the arrow operator. From how the compiler interprets this, it should in principle be equivalent, so we can take a look in the disassembly that in the end you see both lines, while they look different, they compile to exactly the same code with minor differences, since we have different offsets for like test 5 and test 6 are located in different memory regions. So where do we have the difference? Yeah, here. It's slightly somewhere else, but everything else is exactly identical, so there is no benefit computation wise to use the one or the other. Yes, so that's that. Yeah, as already demonstrated here, we can have structures that you can just image one structure on the other, but a more typical approach would be to have a version 2, let's say, my struct version 2, to which we add some additional fields. What would we add? Let's just add some int64, we call it G and H, for example. Oops. Oh, so this is again 8 and another 8. Yeah, and now we can cast our initial variable. Sorry, was war's? Was v2 Strichpunkt is equals and of course, if we do that, as already mentioned, the semicolon is missing. The first fields will be valid, while the later fields, oops, it should be fine. Why is it complaining? Yes, it's missing the reference. So the first fields will be valid, while the other fields will not be, since we have not filled them with anything. So if we look at, we just get, in this case, some garbage in this memory location. And if we activate the hex display, it is this CCC, which is normally with which stuff is normally initialized if you have not initialized it yourself. And what we also can do is we can do another type. Let's call it my struct x. As x or x, but first we need to define that. It will be, we just copy of this, and here, instead of like copying all the fields, we can just take the type. Oops, sorry, that's the wrong one. The other struct. So we can nest structs one in the other. Let's call it v data. Yeah, let's just call it data, and then we have 2 additional fields. That is fine. That is missing here an asterisk, and maybe we should so that we can actually access those fields. Let's a pointer. So let's make it not a pointer. Just let's call it vars2 and then initialize it with new data. So 1, 2, 3, 4, 5, 6, 7. I think we have 7 values which are valid. So let's cast this structure, and on this new representation we can access it. So when you look in this, well, once it opens, you have the other structure as one field which contains all the values correctly, and then you have your new 2 new fields. Okay, I forgot one. So you can create a newer version of a structure also just by adding the old structure, and an extended version by adding the previous structure as a member like this. And if you so in principle this is quite flexible, and the reason why this works is, as said, because internally this is just one continuous piece of memory, and all this naming and separation in variables and which part of the memory means what is just at the level of the compiler. So at this point, when this code gets compiled, any information that we have, most of those fields here, would be gone completely. We would only have the information about the fields which we actually used. So, for example, if you would be trying to reconstruct a struct from a program you don't have the source code for, then you may end up with something like this, with a lot of dummy entries where you don't know what's in there, and even from how many entries it is made up. You would just know that, okay, a given offset you had some value you were interested in. Yes. So what else can we say about structs? So we had already casting. Yeah. Yeah, one other interesting thing about structs is that you can, so the compiler allows you to use them like a machine type. So if we have our extended struct, we can create a new one like underscore b, not as pointer, and you can just assign to it. You can dereference this one, for example. And despite that this is not a machine type, the compiler will internally create you all the necessary copy operations, so we can take a look on that here as well, and you will end up with a full copy of your piece of memory. So we see here that it loads the address of the target into args, then it just moves that into RDA. So the DA and SI registers have a special meaning. DI is for destination and SI is for source. So in the other register it loads the variable we have here, and then it executes a move operation where it puts in the ECX register. So the CX, so generally the C register contains the amount of operations, how many are to be performed, and then you can make with this repeat instruction, you can implement an operation to be repeated multiple times, and in this case it is just a move, or in this case multiple moves. So it will always take the address from the source, add this address copy with how many, what says byte size, okay, that is individual bytes, so that will be a bit wasteful. In principle this operation, if the structure is aligned, could be performed with larger moves. So here really just copies the 28 bytes it needs, but that could have been also like a double word where it would more efficiently copy. I don't know why the compiler is so inefficient here. I mean, I guess it's because it's a debug build. And if we would step through it, you would see that if you are here at this line and you tell it to go to the next line, it would actually be stuck in the line for however many variables there are. So if we write this quickly down, so we have RSE RDI destination RCX operation count, and then we have rep moves, what was it, RDI RSE, and each time it repeats a move instruction, it will increment those both registers by whatever bytes, by whatever size it was implemented to do, and it will decrease the RCX register by 1, and once it arrives at 0, it will then get out of this automatic repeat mode. This is quite useful because this way you don't need to write a loop with many instructions on your own, but you allow the CPU to do all that for you. So if we step now here through this thing, sorry, that's wrong. So we might step, and now when we try to step, we will be stuck in here. But if we look on the registers, we should see them changing. Yeah. So it's incrementing the two address registers and is decrementing the operation count register. And if we click enough amount of time, at some point we will arrive at 0 and then go to the next instruction. Such a thing you could not do on ARM. ARM does not have, from what I know, a rep instruction there. Actually we can compile it for ARM and then just compare. Properties, configuration manager, new ARM64. Okay, I will need to start the other thing for that. We just want normal ARM64. Yep. That is, we need a second. Okay, we need to wait a second until the other thing starts up, because I cannot run ARM code locally. As I said last time, I need to run it on the Raspberry Pi, which I forgot to turn on. So it will take a second or two before that will be up. Okay, it's almost running. Not quite. Maybe it got a new address. That could also be. I haven't used it since last week. That should be fine. Yeah. So this thing is running already. It just needs a second to finish starting. In the meantime, we can finish the configuration of our remote debugging. So we go to debugging, debug ARM64, remote command, that will be what it starts. Yeah, which IP do we have here? Yeah. That is a bit slow. Sorry about that. Did that freeze? That seems to have locked up. Why is that freezing up? Really, that was working. Okay, it is just slow. Let's close the things we don't need. We need this thing we need. So as repos. Structs. Okay, let's compile this quickly. It ended up ARM64. That should have created a new folder. Oh, it's in tile 1. Then let's go to tile 1. Okay, so this will be our command. Remote command, remote debugger, command line, remote computer. 1070.10.1. That should be fine. That should be all we need. Or not. Is in the file directory? Yes. We also need to change the directory to something that it will be able to start in. Well, it's doing something. But it hasn't yet started. Okay, we're almost there. We are missing a couple of files. That will be But we had that already working for, which one was it? Variables, I think. Yes, so we can copy all the DLS from here. Struct SAM64 debug. Ah, great. Okay, now it will start. It's starting. Here probably needs to load a few symbols. Yes. So as you see, the implementation is much longer on ARM. We can now step through the thing step by step. So we start at the beginning. That was why I didn't repeat anything. Yeah, just well, the structure was small enough, so the way it did it was just to make load and store operations with the Dingsbums of 20 bytes at once. So it is not that inefficient, but of course if we would have a longer structure, I mean we can simulate it by just adding for example a few more elements. Before test, let's add, I don't know, 20. Let's go all out. Let's go with 100 elements. That will be like now a huge structure. So if we run it again locally, the code, the implementation will not change, so at least it shouldn't. So you see it is still just the same short piece of code, just that here the number for the repeats is much higher. But now if we look to the ARM version, that it will need at some point to go with a jump. Okay, so actually it just internally used a function to copy memory. But we can, for example, take a look how this works. So now it's really quite inefficient because it even uses 2 copy operations. That is really wasteful, in fact. But like the first copy operation will create a temporary variable just to get the dereferenced value of this, and then in the second operation it will use memcopy to actually assign it to the new address, to the new variable. So as you see, ARM code, because it is so minimalistic, is not okay, and we don't have the source code for the copy function, it can often run into, so it can often be not as efficient in the end, because you just need much more code to do the same thing that you could done using a complex instruction set normally. Did that crash? Oh, that seems that it crashed. Oops. Interesting. That's a bug which someone should report to Microsoft. It should not crash if you press stop. Another interesting thing is that you can, in fact, so first of all we can take a look how this would look in the 32-bit version of the Intel architecture. That will mostly look the same, just that the registers are prefixed with E instead of R to indicate that they are smaller. But the way it implemented it, it will be even the same amount of operations. So, well, the order how it compiled it is slightly different. So it first tells it how many copies to do, but actually the copies here are implemented more efficient because it's copying 4 bytes at once, while at least before it copied this one by one. But also, if we take a look again, I'm not sure whether they... Yeah, it's interesting when it creates the code for 64-bit, it goes with the less efficient one by one copy approach. yeah, well, I said how these compilers optimize things. At least for Microsoft compilers, it is their undocumented secret, and sometimes it's not as good as it could be. If we would use some open source compiler, then we would have more control, or even could go to the source code and change this behavior to make it behave exactly how we want it to behave. But what I actually wanted to show you with regard to this 64-bit thing, that is a small detour. If we take a int 64 a, and then want to assign it to another one, let's say b. So obviously in 64-bit, this must of course work natively because the register is large enough. We can take a look on it. This will be quite weird here. It is just, well, it just loads with one operation into the register, and then from the register writes to the new location. But of course, if we go to 32-bit, then the register cannot hold this much data. So we will see that the compiler will create much a bit more code, but it will still allow us to use 64-bit numbers in our code as if they would be natively supported. And here you see that it is just copying. It's just using two registers, copying the low and the high portion, and then it's wait, which one is which one? If we go to show numbers, the low portion and then the high portion, yeah. This more descriptive, and this is actually quite nice because you can do any sort of operations in 32-bit with 64-bit numbers, and you can just do as if it would be a native object. But I said, of course, in reality, it will need much more operations to do it. But it is quite convenient. And of course, if you would try to compile it for ARM, you would also be able to use this. So internally, it just says that this is a struct with a int high and int low. But I guess I mean, it's good to know that you can use this in any bitness, and the compiler will just take care for you for these. Yeah, and of course that you can copy a structure. An important thing again with the pointers is to know that if you assign something by value, then it really is a full deep copy of the whole memory object. What you could also do is do an assignment by reference. So this is assignment by value. Where you add here an add, and then still need to dereference it. And in principle, this is internally equivalent to just using a pointer. But the difference is that if something was like this, you can use the that one is maybe not the one I want. You can use the dot operator, while with the pointer, as already said, you will need the I need different letters, C and D. You will need the arrow operator. But if you look into what the compiler does out of it, those two are equivalent. Also, technically, so well, are they? Yeah, it does exactly the same thing. One thing I wanted to mention is that technically this is not part of C. It's only possible in C++. So in normal C, you always need to go with the pointer approach. But if you have a CPP file, you can do this by reference. It is of course quite useful when you have a function. Then you can have an argument and pass something just this way by reference, and then allow the function to alter it. And the last thing about structures that might be interesting is that you can also use a structure or create a structure where multiple fields will share the same memory. So like with this plain structure here, we have assigned to different memory regions different names. You can also create a structure, which is in this case then called a union, where you have different names, but they all occupy the same memory range or the same memory location. Now, such unions are usually only useful in combination with normal structs, but you can, in principle, create a union without a struct that would contain it. So or rather, well, let me write down an example. So we have a union. We call it my union, and then we give it a value int64. And what we then can do, we can then inside the union define a structure, and we can either give it a name or not. This is up to us, but for now let's don't. And then let's make int value low, value high. And now the idea is that this member will share the same memory as this. Well, in this case, these are two members. Normally, it should have a name. Let's call it words. But as we will see later, I mean, you could also just put a structure inside another structure, and that would also work. But here, the nice thing is that now, if we assign, let's create a value, my union, and we assign that should be here. We still don't need a name, so yeah, we can assign the value, something long. Let's go with null x. Oops, that didn't type. And now you can access the high and low portion of it like this. So int high, int low. So one will be 1 through 8, and the other one will be 9 through f. And this already demonstrates one for example use case where okay, we need to switch to hex. Where you can use it to in some nice way restructure your data. Another use case, for example, could be that you have a union. There was a typo. My union. The other use case could, of course, be that you have a union, and then you have. So let's make another use case, a more real life one. But before we do that, just a quick look on this on the other one. So union B. The only difference between union A and union B is that with union B, if you want to access what's inside, you don't need to write the name of the other structure. Since you didn't give it a name from the beginning, the structure information is lost, and you can access it directly without using the name that you have assigned for the structure. Technically, if you want to write it down in a really nice way, to be as silo, and then you would here write what was it we called the words. So this is why is it complaining? Oh, sorry, that was the wrong one. I should not maybe delete that just to keep it. Yeah. So this is equivalent to this. It is just more compact written. You can always, when you define a type, after it directly defined, so we could actually skip this step and just write my union here. This is quite nice. And technically, if you are using it to define a variable, you could not give it a name. I mean, then you cannot do any casting or stuff because you don't have a name to refer this object by. But in principle, you can save on typing doing it this way, but it's not nice practice. And of course, if you want to be able to access the elements at the same level, so let's move that further down, union B, then of course you need to nest the union in the structure. But to go to the, as mentioned, more useful use case, you could for example have some structure as result, then you have some int type which tells you what sort of result this is. Then you have a union which does not need to have a name, and then you have in this union different structs. Which don't need a name, but they need a name at the end. Let's call it result A, and then you have a struct called result B, and then you have a struct result C, and let's say this is, I don't know, int A, A int B. This type will have, I don't know, char A, and so on and so on and so on, doesn't matter. And here, I don't know, something. And this way you have defined yourself an object for which you can get the maximum size you will ever need. So const int size of result is like size of as result. So you know that the thing at most is at most 16 characters, 16 bytes large. And then you can pass this to a function, and the function will then set first the type and tell you, okay, this is type 1, for example, and then you know you need to, so assuming, so for example, a use case would be this, sorry, we need to make something of it, so let's call it point. So we would set then type is like 2, let's say 2 represents B. Normally you would index them probably by 0, but let's say that we index them by 1 and 0 indicates invalid type or something like that. Then you go to your result B, and then you set your values as you require, A, B, C, 1, 2, 3, or something like that. And of course, if you would then have a different use case, so let's put that in a scope and then make another use case. So then you would also actually this could be in front, and then you do different things, and then here you could decide to set one that would be A, and then you would of course need to access result A, and you have I think only A and B, and we don't have a C. So this, for example, a typical use case where you can benefit from using unions and nesting different structures within them. And of course you can have an more or less arbitrary depth of this nesting. You could of course define these structures here explicitly, so you could say structs result A, then here you would write result A, so this is all equivalent. Depending on your use case, if you need them to be explicitly available somewhere else, or if you want them just to be nested internally. Yeah, we can also create another nice union. So for example, with the homework you had the very first time where the goal was to break apart the floating point number, you could have used a union to do that. We maybe will not demonstrate it here since some people didn't turn it in, but I can show you, for example, how you could break apart something that will contain different sizes of integers. So we could create an union. Let's call it my int union, my integer union, and then we have first char this. So that's the cheapest single byte representation of an integer. Then we have a struct which we call part 16. So this will then contain shorts, value low low, low high, slash h, high low and high high. I mean, we could of course this represent differently. Let's call it shorts. That's 4 shorts. Yeah, then we could represent it by another struct. Sorry, another union, which will contain one struct int u low and value high, and then like here, just with a long. We can use int and long is here the same, so we can use it like this. It's missing here a strict punct and it needs to be called ints, and of course we have the int64 type, which is just on the value. So it's quite a nicely structured way to break something into its internal representation. Let's call it this way. So let's use it. So we have this. Let's call it my int. We can initialize value to. We had it somewhere already. No, we didn't. I thought we had it somewhere. Yeah, this one. Instead of typing again, we just copy it. And when we run this, then we'll see that through this nice structure, nice use of structures, we have everything quite nicely structured. So our value low and high. I did not give a name to the other one. This one doesn't have a name. That should be called parts 32. But let's ignore that for a minute. So we have those, they should be in parts like this. And if you see, then it really just correctly separated our one large value into whatever representation we want. With ints we have of course here, so with part 16, what was other shorts here? Yeah, anything where we did not look inside? No, that's fine. Now let's rerun it with the right parts 32 added. So in case so for those of you that did not yet submitted the first homework, you could try to use a union to break your floating point number apart, and that would be actually quite nice if you manage to do it, because that's cool. That's the way the pros do it. So now we have the right structure. We have the ints with the ints. We have the two parts. We have our shorts with the shorts. We have parts with the other thing. I mean, this is here maybe a little bit over verbose. You would either have only parts or only shorts. You would not go to this length to make all the different representations.
Sorry, can
Yes?
I ask a question?
Sure.
Is the difference between union and struct? You can use a union to have a struct and or multiple structs as well as variables inside, right?
So a struct, every member in a struct gives you a new memory location. The memory locations are one after the other, with maybe some gaps introduced for alignment purposes, but every member has their own memory region, while in a union every member starts at the same memory region. So maybe we should write down the addresses here. So let's say so we start with a union. So let's say this has address, I mean, we start with 0, of course, 0, till we have 8 members, so 0 till 7. This will be the offset. So an address is usually made up of some address, some base address plus an offset. So here we just write down the offsets. Now, then here we have a union. So this struct will again start at 0 till 7. And here inside the struct, we have now a normal struct. So here we will start giving individual address. So this is 0 till 1. This one is 1 till 2. Oops, that was one tab too much. So this is 2. Wait, 0 and 1. Yeah, 1 and 2. 2 and 2 and second 0 1. That should be then 2. Sorry, 2 and 3, 4 and 5, 6 and 7. And then we are here again at the union position. So here we again have just 0 till 7, because it's the same entry, just in a union. Then we have the next union. So this union again, since this union is in another union, will start at the same offset. This thing, since it's in a union, starts at the same offset. This is in a struct, so this gets own value. So this goes up to 3, and here it goes from 4 to 7. Jawohl. This again starts at 0, like this one, and this one, since it's in a union. This is maybe not, I mean, it doesn't have much variety, so to say, but I think this demonstrates, and we can maybe make this a bit ein bisschen einrücken to make it look better. So the struct always increments the offset counter, let's say, while the union for every member starts at 0 at the 0. This way you can define that multiple different objects will share the same memory. Of course, so in this use case, any member of this union is valid. In the use case here with the different results, always only one of the 3 results would contain valid data, while all the others would contain garbage. And then you need, of course, something. So here we could also write down the type. So we start with a struct. So this starts 0 to 4. This union then starts at, the whole thing was 16, right? But the character int well, it starts at sorry, that's not 4, that's 3, and that's at 4 till 16, so that will be the 15th. Yeah, and inside this union, every member will start at the same range again. For the rest one, I don't care. For this one, what will it be? It will be 4. Well, it's just 4 because it's just one thing. Then it will have 5 till 7, because it has the hidden fields. Then it has here an integer. Wait, oh, that's too much. No, that's fine. 8 till plus 4 is what is it? 12. No, it goes always to 1 less. 12 is the next one. Till plus 4 is 15. Yeah, here is something whatever. This structure, since it's outside, it will of course start at 0. So this is here just 0 till 3 and 4 till 7. And of course, if it would be here, then you would add 4 because it starts at 4 to it.
Okay, so for such a structure like the one below, you will always have some, in this example, the value, which is basically our data. And because we use a union and always access the same storage bits, we basically, the rest of it is all only looking onto the data, right? Because we always
Yes,
start from the same location.
exactly.
We will always use it like this. So
Exactly.
one is our data set and the other one
Mhm.
is accessing it.
It's just different representation of the same dataset. So
Okay.
if we, for example, here go to value bytes 4 and change this to FF, we will see that even though we only accessed one of the many members, all of the unions. We go to locals. Okay, we have too many locals. Go to watch. This thing is called my union. Then we see, okay, so bytes we changed here to FF index 4, but in the all other representations, so here the index 4 would be here, so it's changed here. It's also changed here. Well, okay, index 4 maybe was not the best example, but as you see, it was changed everywhere in all of them because it's always the exact same address. Another way to see it also, you can use here the immediate window, so we can go address of this, so this is our base address, and we can cast it to avoid asterisk to not be bothered by the different by the content. And now if we would go to, for example, punct bytes, then we get the same value. If we go to another member, for example, that was part 16, we still get the same address. If we go to which one want we? Let's say parts 32 punct value low. It will still be the same address because it's still 0. But if we then go to the next one, then it will of course be incremented by 4. So 8 plus 4 is C in hexadecimal representation. And if we would do the same, but just go to part 16, that should be, what should it be? Value high low, I think. Yep. We then again get the same memory address. And as long as we change something at the memory address, everything that refers to this memory address will of course see the change directly. So this is one nice use case for unions.
I would then
Yes.
also have a question. So why then, if it's already starts with 0 for the outer union, why do one need the inner union?
To add structure. So yeah, in principle you're right. We can just get rid of that. We could have given this a name, so we could have called this here yeah, we already called that shorts. Yeah, for example, we could have called this shorts in this data, and this gave this a name ints, and this a name, yeah, again data. We can reuse the name because it's then in a different spot. But you are right, in principle, if we wanted to create the thing we created, we could just get rid of this union. They don't fulfill any purpose in this case.
Okay, good, thank you.
Yeah, zack. Yeah, it just was kind of nice to group it by the size, but in this case it's fine. Okay, so this match to this, and yet another very useful use case for unions is to manipulate flag fields. So in the first or second lecture where we looked at variables and operators, so I told you how you can set or clear a single bit from a variable, and explained that this is usually used to have flags, so give meaning to individual bits or individual pairs or triples, or well, of amounts of bits which are smaller than what you would usually have as a machine type. And what you can do with a flag, what you can do with a union in order to make this flag operations much easier is the following thing. Create a union, my flag union, for example. I mean, the names, of course, you can call them whatever you want. I just It somehow is customary in all this literature you read about programming with beginners guides that you call something my something. So I am just sticking to it. Int flag. So first of all, we define some initial memory where we want to have our flags. Then we make a struct. We don't give the struct a name because we want to access everything at the same level as the flag field. And then we can use a feature that actually would have worked also without the union and the struct, but it's much more convenient if we use it. We can define names for single bit ranges inside a machine type. So let's again start with int. Let's write down that we have 32 bits to play with. So we have first byte, and then you, instead of just finishing with this, you just make double point, and then you write down how many bits you want this particular variable to have. Then let's go with another byte. Let's call it byte 2. Again 8. Then let's use some nibbles. Nibble 5. That's just a 4. Nibble 6. Okay, that's so of course 4. Then nibble 7. So I make always a space whenever we go from one byte to the other. But this is just for presentation. It has no meaning. In principle, all of that could be just written down. Oops. In a terribly unreadable fashion like this. As I showed and mentioned at the beginning of the first lecture, C is in this way very tolerant, so you can make really terrible code if you really want to. So that's bit 29 at this position. That's of course 1 bit, and then let's go 1, 2, 3, 4. Wait, that was 1 too much. Okay, and apparently the auto formatter wants us to make a space. So the new version of Visual Studio, yeah, okay, it makes it hard for you to format the things you want them to format, because it kind of tries to enforce one standard on everyone, which in a way is okay, but I don't think it's really the prettiest thing. So I like things to be like aligned here to the line, but the standard formatting kind of just goes for the same space but ignores additional yes, and the last one doesn't have a comma, but a semicolon instead. And when you so there is a setting you can disable it. Normally on what? On paste, on semicolon, and maybe even on new line, it will format the code block up to the wherever the scope starts that you just finished. But anyhow, the nice thing about this thing is that now we can access individual bits of our flag, but access them without having to think about at which offset it is. We only need to define here our positions correctly, and then this is all we need to do. So let's start. First of all, let's check whether the size is really as it should be. No, first let's define it. Let's call it var fu. Then const int var fu size of var fu. So let's check. It's 4 as expected, and now we can start setting things. So we can first of course assign all of the flags at once by assigning the flag field. So let's null x 1 null f a b I don't know, something like that. And now let's say char test1 is equals oops, byte 1. Then we can of course have char test2. I mean, in principle you can also use this of course to assign values, so we can say byte 2 is now equals, I don't know, why not, 0xff, and so on. So in principle you can access, for example, let's access the lowest bit. So for example, you could have some if what was it, var fu.bit this, then I don't know, return 1 or else return 0. So this is a really nice trick to give structure and represent it in a nice way, something that normally you would only have as a bit field, where you would need to use the various bit shift operators to access all the positions in this flag, in this union. So since you all should already have some experience with bit shifting, let's quickly copy here a use case for our flag and invent some homework. So what do we say? Code block start. Homework. So the homework is to just access all those individual members or assign values to them, like demonstrated here. Okay, yeah, we assign a nibble here. We assign 2 values. We get a value at. Sorry. Yeah, we. Why did I route that? That doesn't make sense. That is boring. We don't use. Okay, it's fine. We use it as a demonstration of assignment. But for the purpose of the homework, I just stick with that. Yeah. So this should be easy enough. It will give you some practice with regard to manipulating to do this different bytewise manipulations, and it also will give you probably some appreciation how much less typing you have if you use this trick with the union. That is I think a good exercise, and that would be everything to structures and unions, unless I forgot something. But I think I didn't. Yeah. So in principle we should now start with a function. So we have 45 minutes left. So I guess we will just quickly start, and then we see how far we go. Unless there are any questions with regard to structures and unions that still need to be urgently answered. Okay, there don't seem to be any questions. So let's save this and create a new project. We can close this. Create a new project. Next, functions. Oops. Should be type free now. Okie dokie. So well, we already have seen one function like this main, and I think I used printf in some other places to print some text on the screen. So in principle you already have experienced functions in one way or another, or you have seen them in other programming languages. So I guess we don't need to talk on a more abstract way what a function is, but start with writing down a first C function. So first of all you write the return type. So let's say I want something that returns an integer. We call then the function name, we call it my func, just as my function, and then we can specify a few arguments we might want to give to the function. Let's say integer a and integer b, and then we make a curly brackets a code block which then will be the body of our function. So let's make it a super simple function. We let it calculate the sum of a and b. So let's call it c. Let's make a plus b, and we want to return the value such that it can be used. So of course we could just also just write this and don't have a temporary variable, but for now let's stick with this notation. And to call a function in C, first we will need something to give the function. So let's define two variables, int a1 and b2. And the function call is quite simple. You just write the function name, my func. Oops, and then you can write the arguments a and b. In principle, you could of course write the number directly here, 1 and 2. That's also fine. Let's make another variable, and of course if the function returns a value, then the value can be, then you can get the value, just assign your function result to any variable. We could of course use this here. So there are many simplifications that can be done if one wants to. So let's put a breakpoint on our function and take a look how this function looks, how it's implemented in the compiler, by the compiler. So you see that we have two move operations into two registers. So it puts the first argument in the register ECX and the second argument in the register EDX, and then it uses the call instruction to jump to wherever our function is. So we can step through that quickly. And if we step then okay, here the compiler created a jump table which we don't need. There's a lot of shit we don't need. Let's quickly disable all that we might find annoying. So we don't want this. This is fine. Preprocessor, code generation, we don't want any of that. And we don't want this either. Okay, that should create a much nicer code. I'm not sure where to disable this jump table creation. So the idea at this point is that if we would edit the code, then in principle, so if we would add like +3 and then try to make a step, then the thing would recompile it and then just put another copy of this function somewhere in memory. And what it would then change is that if we do this call to this address, at this address we have only this so-called jump table. So it is just a memory location which contains a jump instruction with another offset, and this is what the compiler would change. So it would not like overwrite the old myfunc, it would just create a new myfunc and then point the jump table to the new destination. That can be disabled somewhere. But once we did that and follow the jump, we arrive in our function. So here you see that it copies the two arguments it got in these two registers onto the stack, so into memory at a specified location with relative to the RSP, so to the return stack pointer. You may notice that the first value that is copied already has an offset. The reason is that the call instruction, as soon as it does the call, it puts on the stack the address to which in the end we want to return. So if we take a look here at the RSP will contain this is a void Stern. Yeah. So if we get the value of memory that RSP points to, we see that the stack pointer points to a memory location which contains the address in our main function line 18. That will be well, that's the right line here. And yeah, and if we now step through the function, so we put some things on the stack, then here with the push instruction we will be saving the value of the RBP register to the stack. This will increment the RSP register. So if we look here, where's this RSP? If we execute this instruction, RSP got incremented by 8. That should be. I have not remembered what it was before, but we'll step through the function again. Then, once we did it, here we subtract from RSP. So the stack grows, as it's called, it grows downwards. So if you subtract something from the stack, this means you are reserving new until now unused, or at least not well. It might have been used by something before, but currently it's unused. So new unused space. And when we do this, 50 is how much is it? That will be 10. We should be able to store up to 10 64-bit values on the stack from now on. Now we don't use most of it. I don't know why it's going with 50 from the get-go, but that's an implementation artifact of how the compiler does it. What we then do is we set the new copy the stack pointer value to our RBP, to our base pointer. This is used when we disable this symbol naming here, because the RBP will be used for addressing. So if the function would do other calls or put other things on the stack, the RSP would then change again, but the RBP only changes if we want it to. So this way, as I think I already explained that last time or the time before that, the nice thing of using this is that you always can use the same offsets. But as also said back then, it's not really important for the user, because you are not. It is fine for you to let the compiler just keep track of the offsets. But anyhow, so we have prepared our base pointer. Now we can do another step, and here we are then getting the data from which we before. Wait, why did this? It changed when I switched something. Because before we were saving those. I will restart it quickly. Something changed too much. One moment. So we are here. Step, jump. Yeah, I don't know. It cut those 2 lines off before when I was stepping through it. Wurscht. So let's again step through it. Step. Okay, we were here, and now it in principle again loads the same value. So if you go with the offset 50 and 10, that's 60, and 50 and 8, that, so is it correct? It's the wrong direction. RSP is stack pointer ECX. That should be the first one, and the second one. No, that's the wrong direction. This is the second one. So it loads the same values just into different registers. Once we let him do that, we should have, I think, 2 here and 1 there. And now the next thing what it does is it loads again the address. Why is it doing that? It doesn't need to do that. It should somewhere do the addition operation. Okay, x plus die. I don't know. It uses the layer instruction to do an addition. That is really strange, because there is like a dedicated add instruction, but what it here does is it kind of, they try to optimize it somehow, because here you can with one instruction apparently do an addition of 3 operands. The result will end up in args. I haven't noticed that the compiler does this optimization before, but it should of course contain the right result. If we remove, I guess this +3, which we added just to demonstrate this hot recompilation thingy, then I guess it will not. It will use just a normal add instruction instead. Let's see if I'm right. Yeah. So now it just uses a normal add instruction. The way that standard instruction work is that they have a accumulator register. So it is an operand and the result for the operand. So it's in a way destructive, because it takes the value from EC, it adds to it the value from EX, and then it stores the result into EC, back into EC. The way this was used with the layer instruction, which normally is not intended for such use. So layer stands for load address, and this is quite a really peculiar optimization. I have never noticed the compiler doing that before, but good to know that it does such weird things. So anyhow, if we step through this quickly, we will see that after this line, the ECX contains our results. So now it's just 3, since we don't have the other 3. Now the thing moves the result to the EX register, because the EX register is defined as the return register. So when you have a function that returns a value, if the value is of type integer, then it will be returned in the EX or RX or RAX register. So as I think I already said with variables, if you have here an E or an R, defines how long the register is. So if you know that you only need the first 32-bit, then you can use the EX notation, and the the high bits will be reset for you automatically, while the lower ones will be copied. And then here it also stores the result into our memory, but this will actually never be used. Well, it's not optimized, it's really wasteful. So it stores the result into EX, which is the return register set, but then it saves it to memory just to, in the next line, load it from memory again to the same register. So if that code would be run in release mode, the things would be much more optimized. So maybe we should do this as well. So I think then now I need to again configure this something. So let's see. General no optimization, but we don't want too many optimization. But if I disable all of them, I guess that will not be that nice. Code generation, this we don't want. This we don't want either. Oops. Okay, let's see. So ideally, of course, you could write such a function much shorter if you would do it by hand. So again, we stop in here. You can also take a look at the RSP register, that as soon as we do the call, the register gets updated. Okay, so for example, in the release build, it did not create the jump table. So it was already one step less. Here it still does this storing and reloading from memory. So let's add some optimization. Let's go with the default. At this point, it could of course remove the function entirely, which it did. So here the optimization was basically just actually the optimization was just throw away everything, because we don't use the return value. We need to use the return value for something. So the optimization the release build might be quite annoying, because they tend to throw away. Okay, it actually implemented the whole operation in, like, it knew if we add 1 and 2, then the result will be 3. So the optimization is to just return 3. And that is too much. Okay, there is a function that gives you random numbers. It's called rand. Okay, now this, but then it will still remove this function here. I guess it will then just collapse everything to just return a plus b. Yep, it it just removed the function entirely. So I guess we will not see a optimized version. I mean, we could. What could we do? I don't know. We could try something. We could make we could make it think that it needs the function. Something like that. If we use the function more than once, it should not remove it as an optimization. Well, it still did. Damn it. Oh, let's make more. That should. Yes. Okay. That was not optimizable anymore. Okay. So we step into the function. Great. I did it. Call stack. No, it's still inlined. We have the call to the rand function, but it's still have move. Another call symbol names. No, it's still optimized too much things away. I mean, there would be ways to force it to not do the optimization, but I think for now this is not. I don't know. Principally, if we use the function twice and have it use a rand instruction inside, that should. But it optimize it away. I have no good plan how to force this other than by disabling the optimization. But if we disable the optimization, maybe there's a special setting for function inlining. Oh yes, disabled. That solves it. Now it should keep the function. Yes, okay. We can make the function be simpler again. Yeah, so we have wait, but now it's still inlined it in this. If it was so simple, okay. Then let's go with the more complex function and this inlining turned off. Yeah, so this works now in a much more optimized way. So you see you have much less instructions. So here we still save RBX. So RBX is one of the registers which need to be saved. That's the next thing that I will tell you in a second. Then it saves another register which it will use. Then it creates much less free space on the stack for its operations. It moves the data to other registers. Then it calls here the rand function to get a random number, and then it makes, what did it make? It should have made an add somewhere. It did not. First it needs the multiplication, but then it should do addition. So it's somehow still optimized to some extent at least, because now we are missing the add operation. Interesting. What do we have in EX? Move, subtract 20, multiplication, return. Here is the add. Yeah, the code is not longer really well aligned with the individual lines, so it just put somewhere to work, but in principle it does everything it needs. So it calls the rand function. The result of this, as I said, will end up in the RAX register, or AX register, since it's only 32-bit. It will multiply it with EBX, which it filled with our B value, and then here in principle it already says return, but in reality it still has some operation, so it restores what was in EBX initially. It adds A to our preliminary result. It restores the stack by adding 20, so that the stack pointer now is pointing at whatever here was in. Then it restores RDI, and then it makes the return instruction. So it is optimized, but it's quite jumbled, all, how to say it in English, durcheinander. It's much more difficult to trace optimized code, because it's not longer really just a representation of your code lines, but just something that functionally does the same thing. So let's go back to the debug build, as this is much nicer to look in. So as mentioned, there are with the variables, there are many registers that you have in the different architectures, and some of them are defined volatile and others are defined non-volatile. What this means is that once you enter a function, the volatile registers you are allowed to change, and you don't need to care about them, while the non-volatile registers, if you change them, you need to remember to change them back. And this changing back is done using usually this pop and push instructions. Of course, you could also use a move. So if we again enter here into our function, you see that it uses a so what the push instruction does, it takes the value that is stored in the register, which is given as an argument, saves this value into the memory at the position the stack pointer is pointing to, and it increments the stack pointer by, or rather decrements the stack pointer, because it grows downwards, by the size of the register that was saved. So if we step through this again, you will see that as soon as we make push, here the stack pointer register has also changed. We should maybe step through it and write down the numbers, that then we see that it really is doing what I'm saying it is doing. So if we again go into the function, so we are in it. Sorry, let's do the jump. Okay, we are here. So the instruction pointer is always changing, because it is just the address where we are right now. But the RSP was this. If we now make a step, then make this minus RSP. Oops, X. We see that it really was incremented just by 8, as said. Using, of course, a move operation is also an option, but it needs, first of all, it does not increment the RSP. It just copies, so you would need to first move the RBP into at a given position from your stack pointer, and then in the second step, in the second operation, explicitly increase or rather decrease, subtract 8 from your stack pointer. So this push and later on pop instructions are quite nice, because they combine multiple things in one. So this is also one of the reasons why the x68 architecture can be quite efficient, because you can really do a lot of with very little code. Yes, and now if you might already wondered, so what if we would have more than just the two arguments? Where or how would they be passed to the function? So the way this works is that the first 4, so the way this works depends on the architecture. So on the x68 on the x86-64 architecture, so the 64-bit version of the Intel architecture, you have only one function calling convention for integer values, which stipulates that the first 4 parameters are passed in registers, and all additional parameters will be passed on on the stack. So we can make a sample function that does that. So let's just change our function here into one that takes more arguments. So let's make it take C, D, E, F, G, H. How many? That's enough. And now just call the function with, so we don't really care for a return value. Just okay. So now when you look on it, you see that the call here, it starts here and it's placing the arguments back to front on the stack. So it starts with the last one and it puts it on the stack on the right position that's expected by the function. Then it so it will be approaching like more and more towards RSP plus 0. And in principle, you could imagine here like those 4 arguments be also passed like would be the next 1 8 1 0 0 8 and 0 offset. But they are not, they are just put into registers. The idea is of course that this way you can save on operations. So if you really have just a few registers, you can just a few arguments, you can just put them into registers and be done with it. But the function normally internally, when you enter it, what it does is it will copy those values again into the space that was where is it here. Okay, I'm trying to find the function. Let's go with the Cosstack. So as you have seen, it goes down to 20, but it does not doesn't go to 0. So there is actually some additional space on the stack here reserved. It's called the home area or scratch space, which would allow the function to copy, if it wants to, those arguments into this area from the registers. And of course, if we have the debug code which is not optimized, the functions will always do that. So you see here that it's really copying it, but you may also notice that now we have again the number 20, which we already used. But of course, because of the call here, our RSP was decreased by 8. So if we want to access the next slot that we would have here, we would of course need to add 8 again to our first address, which we do. So we again reuse the value 20, then it goes down 8. So our RSP plus 8 is the last free slot that was reserved for us, so to say. And then the RSP plus 0 is the address where we want to return to. So as said, the idea with this call mechanism is that the call instruction will so a call instruction can be imagined like push the rip plus whatever long is it plus 6 on the stack and then make a jump to the call. But it's again here just combined down to be in one single instruction. And of course, if you would have a release build, then if those values are not used, then they would not. So if the values are not used, then the compiler would not copy them into memory unnecessarily. It would just directly use the registers, or maybe it would copy it from the standard registers to another register because it optimized it and decided that another register would be more suited for some of its operation. But in general, this area will always be reserved, and in principle it is not wasteful to reserve it, because when you are in the calling function, this area is reserved when you here prepare your stack space. So you just prepare more of it, and this is fine. It doesn't have an impact on your on the speed of your computations or on the speed of this operation, how much, if this is 80 or 100 or whatever. So and it's also not very wasteful, since it is just how many is it? 64. Yeah. No, 32 characters, 32 bytes that it wastes at this place. Now, if you have and if you have any additional higher amount of arguments, it would just have more and more and more here lines of code where it puts those values into these registers. Now, you may, of course, as a next thing, ask, what if we would have not integer arguments? So let's test this. So let's make one of them a double. It will now use a different register. It will use one of the I think MMX registers, because those are intended to hold doubles. So yeah, it uses here the it's written like from the back MMX XMM1, but the other registers are the same, and the whole calling convention still remains the same. So if we would add more doubles, we would just use a different register, but other than being a different register, it would still use the same layout of memory. Now here we see that it needs here it makes a conversion from the numerical number to, it fills the register and then only saves the register, and then it repeats it for all of them. But other than that, it is very similar in operation. And of course, if we would have a different return type, so if we would return double, then also the return register would change. But it, at least in this calling convention, is designed such that when you what did I press? So here return, it's the MMX0. So here it reuses, I think, the first register. So this is slightly different. So it's not completely symmetric with the use case of integers, because in int you had here let's take a look again. No, actually it is, I think the first one was ACX. No, it's not. So here you notice that you have ECX, EDX, and then these two higher registers, and while the return value was the EX, while in case of everything being double, the MMX0 register is used for the first argument, and then it is also used to return return the parameter. So this is a small detail to keep in mind, that that this value will also change. But these registers are of course defined that they are expected to be changed. So yeah. Another thing that is worth showing is that you can also create functions which have an arbitrary amount of arguments. So this you do just by specifying these 3 dots instead of additional arguments. And the reason that you want to have compatibility, so the reason why they in the Windows calling convention for x68 decided to always mandate that this space of 4 slots will be always kept before every function call is such that you can, inside your function, copy the data, as we will see now in a minute, as we already saw in fact earlier. So you have your data here on the stack, then you enter at some point your function, and the function can then copy the data still on the stack. And at this point, what we have created in memory is a consecutive area which contains our values from 1 till 8, so we can address them quite easy. So RSP int64 asterisk and if we take this into grammar, I think so null is the return address, -1 was it 1? Yeah, 2, 3. So if you take the right offset, you can then just go. Okay, 8 was too much. 8 is no longer valid. You can go through all of them. So normally such functions with a variable argument count will either take here just a count that tells the function how many there will be, or they will take some more complex data from which the function, based on its internal mechanics, will be able to figure out how many arguments there are. There will be. So for example, the simplest example would be this printf function we already have seen to print text. You can give it test percent blah percent f and everything that starts with a percent and then that should be a percent is interpreted. Okay, here d, that will be a digit, that should be something, I don't know, an integer number, and f will be a floating point number, so 1.34. And by passing this string, printf knows what and how many data to expect here. And for the reason to make this efficient, they decided that every function call should keep this space such that the function can copy the registers and then have all the arguments as an array in memory. This is quite nice, and in the 32-bit version of the of Windows, you have completely different calling conventions. In fact, you have quite a few of them, which we will not be taking a look into today, but maybe next week. And the standard calling convention always passes everything on the stack directly. So if you, well, actually we can take a look on it quickly maybe. So if we switch to 32-bit and have R1, 2, 3, 4 up until 8 and then run this thing, then you will see that all of them are directly passed on this. So in here it even uses the push instruction to simplify things, and just puts everything on the stack in the same order basically as it did in the 64-bit version. But of course this then means that every function needs to again read from memory, so they cannot make them so highly optimized if they want to. But we can switch that to a different calling convention. That was it fast call? No, I think it was fast call. Oops, I think it was fast call. Sorry, wrong order. Let's see if that was fast call. They are like fast call, standard call, C call, and vector call. Okay, no, it wasn't fast call. Maybe it was vector call. Nope, but it seems to ignore this setting. It should have used different. Why is that ignoring it? No, that was fast call from what I have in my notes. Yes. Of course, if it's a variable argument function, you cannot use a fast call or other calling conventions because you need the data to be consecutive in memory. So that's why it ignores that. We need to go back to the explicitly written down version. Actually, the compiler could maybe complain now if we use the wrong calling convention for the type. Okay, yeah. So here you see that it looks much more like the x64 calling convention, just that it only puts 2 arguments into registers instead of 4. And the reason simply is because there are so few registers available to you. Another thing that is worth mentioning, since we're already looking into calling conventions, is that when we use so the standard Windows API calling convention is standard call, and here this is a bit annoying the way it's implemented, because you see you push things on the stack yourself. you make the call, and once you enter in the call function and execute the function what it had, here you have where was it? Yeah. At this instance you have this return instruction, but it takes a number, and the number represents the amount of arguments that you had earlier. So when this ret technically it's a ret n will be executed, it will not just remove the one entry with the return address from the stack, but it will also return 20, so it will also remove 20 more bytes from the stack. So the idea is that the called function is responsible for cleaning up the stack after the call has been executed. Well, when you use a normal C call, no, what was it? CD call. The cleanup, the stack cleanup will be done by the function that was called, by the main function. So if you see here, now it's different. We have call, and after call we are adding values to the stack pointer. 20 again, because we have in total 20 bytes. No, it's not 20, it's 20 hex. That's what is it? 20 hex is 32 bytes. So this is the difference between these two calling conventions, and when you are calling a function you need to know which convention to use, because otherwise, of course, here if you would call a CD type function but think that it is a C call function, and after the function has changed the ESP already, you would change it again, and then the pointer would be pointing to the wrong memory. So it is always important to use the right calling convention. And now, of course, the compiler, for the most part, takes care of this for you. So you have just your function with a certain calling convention, and the compiler will automatically apply it when you call the function. But what you, of course, can do is you can create a pointer to a function. So yeah, but maybe we should use function pointers during the next time. Yeah, there are still many things to say about function pointers. But what you can do, let's quickly try it. You can define a function pointer, and if you with a calling convention, and if you then use the wrong one, and then assign to your pointer the address of the other function, and then call your function pointer suck, then you would end up with invalid code. So this is not, of course, a very fabricated example, but so normally when you have a DLL, so a library which contains some code, then the way you are obtaining addresses, function addresses from the DLL, is by using a Windows API which just returns you a void pointer, and then you need to cast that on the right function type. And it is a common source of programming errors that when you load a function from a DLL this way, that your local definition is wrong, and then you are casting it on the wrong type, and then the compiler will implement for you the wrong type of function call. Now this is not so critical with 64-bit, because there is just one calling convention, this sort of fast call approach, and in fact you can leave those keywords in to make your code compile on both platforms, but for 64-bit this will be just completely ignored. Yeah, I think we need to end for now, because we are running out of time. There are only 2 more minutes left. I think during the next lecture we will make a I will repeat most of the function thingies in more detail, because other interesting things is, for example, how the function, how you can pass a structure to a function. So how this would work. Obviously you cannot use a register for that, but in fact, there are ways around it. You are just basically the compiler will implement for you pointers and make some copies of the objects. But we'll take a look on this during the next lecture. Are there any open questions with regard to what we had already, or not? So if no, then you can of course come up with some questions for the next time. And yeah, and as I said, since this is quite a convoluted topic, we will take a close look, and I will repeat most of those things about function calls again in more detail during the next lecture. Now that was just a quick introduction, since we had 30 minutes only to spend, and I think to hear those things twice is also quite useful, since it helps, I guess, to make the things sink in better if you hear them twice, once just quickly glance and then again in more detail. So if there are still no open questions, then we are done for today. No questions? Everyone happy? No one says yes, so I guess not. Yeah. Maybe one more thing to say. This whole stuff may look complicated and maybe a bit scary, but as said, normally, for the most part, the compiler does most of those things for you, so you really don't need to worry about those things. It is just important to have some general understanding how those things operate under the hood in order to be able to write efficient code. So since the time went out, we will see each other next time, and have a nice weekend. Bye bye.
Bye. Thank you.
Bye bye. Thank you.
Thank you. Bye.
Next weekend.